Hello viewers, welcome to this course on mathematical finance. You would recall that in the last class we talked about options and we looked at some of the basic properties of option. In particular, we looked at how we can make use of the no arbitrage principle in order to prove a very important result, namely the put call parity, and then we stated that particular result in the case of dividends. So, in today's class we will discuss a few more results on several properties of options, and we will begin with a particular property in case of American options. So, accordingly, now as I mentioned towards the end of the previous class that in case of American option, given the nature of the American option, that is you have a right to actually exercise any time on or before the expiration date. So, you no longer have a put call parity in terms of equality, but rather you actually have an inequality which you call as the put call parity estimate. All right. So, we can state it as follows: the price of an American put and call option with the same strike as I had assumed in the previous case of European options. So, we assume that they have the same strike and expiration on a stock, and as before we assume the stock pays no dividends. So, on a stock that pays no dividends satisfies the following estimate, that is S0 minus x e raised to minus r t greater than or equal to C A minus P A. Remember, C A and P A are the price of the American call and put respectively, and this is going to be greater than or equal to S0 minus x. All right. So, the proof for this again will make use of the no arbitrage principle. So, first of all we assume suppose that the first inequality does not hold. So, by this I mean that I assume that this inequality does not hold. So, this means that I am assuming that C A minus P A minus S 0, that means C A minus P A is actually greater than S 0 minus x e raised to r t. So, this is C A minus P A minus S 0 plus x e raised to minus r t is strictly greater than 0. Then what is the strategy I am going to adopt? That means that at some time t is equal to 0, first of all we will sell a call option, then secondly we will buy a put option, right. Both of them are American call and put, and then thirdly we will buy a share, right. And what we do is that with the remaining amount, that is, so when I sell a call I receive an amount of C A, when I buy a put I spend an amount of P A, and when I buy a share I spend an amount of S 0. So, this amount is invested at rate R. Okay, now at some small intervening time t, maybe which could be also equal to t, suppose that the holder of the American call Remember, you had sold an American call option, so that can be exercised any time on or before capital T. So, you now consider the possibility that yes, indeed the holder of the American call decides to exercise the call option. Then what will happen? First of all, when the call is exercised, so that means that you will receive an amount of x for the share. All right. So, this means that your position under the call option is now covered, and the share you had bought, you have managed to sell it off, and the put option that you had bought, that sort of goes without exercise. So, you end up receiving an amount of x for the share. So, now again, so at that point, if you decide that you want to actually withdraw, so here the net investment is equal to 0. So, here the net amount is that you first of all you receive an amount of x for the share, and secondly you had invested Ca minus Pa minus S0 at rate r. So, this you will receive the amount Ca minus Pa minus S0 with the accumulated interest. Remember, this is times small t. So, the accumulated interest will be given by a factor of e raised to r t. Hence, your net gain is going to be Ca minus Pa minus S0 whole thing into e raised to r t. Now, this can be written as Ca minus Pa minus S0 plus x e raised to minus r small t into e raised to r t. Now, we just observe that since t is less than or equal to capital T, so therefore, e raised to minus r t is going to be greater than or equal to e raised to minus r capital T. So, this expression means that this will be greater than or equal to Ca minus Pa minus S0 plus x e raised to minus r capital T into e raised to r t. And remember that this quantity, by assumption, this was a positive quantity. So, this means that this entire exercise, this value, this is anyway is positive. So, the whole thing is going to be positive. So, this means that we have an arbitrage, and so our assumption here is incorrect. So, that means that the first inequality is indeed actually true. Okay, now, I suppose that the second inequality actually, namely this one, does not hold true. So, in this case, what will you assume? We will assume that, so for the second case, we suppose, so what is the assumption? I will assume that Ca minus Pa minus S0 plus x, this is going to be less than 0. So, I assume here Ca minus Pa minus S0 plus x is going to be strictly less than 0. So, then what is going to be my strategy which could lead to arbitrage? So, at time t is equal to 0, what we do is we will first of all sell a put, secondly we will buy a call, thirdly we will short sell one share, right. So, this actually I can view this as being equivalent to Pa minus Ca plus S0 minus x is greater than 0. So, when I sell a put, that means I will receive an amount of Pa. When I buy a call, I will spend an amount of Ca, and when I short sell one share, that means I will receive an amount of S0, and that means that I now can invest this amount at rate R or borrow in case this is a negative quantity. So, now suppose, now here you have sold an American put which could be exercised at some time. So, at some time t less than or equal to capital T, if the American call is actually American put is exercised, then what is going to happen? In this case, that means that you will actually have to buy the share. So, you just first of all you will buy the share. So, that means your position on the put is closed and you are short sold the share. So, that means you return the share to the owner, and then you receive your return on this investment. So, that is going to be P A minus C A plus S0 into e raised to R T. So, that means what is going to be? So, in the first case your net is equal to 0, and in the second case your net profit is going to be, so you have received this amount. So, it is going to be P A minus C A plus S0 into e raised to R T, and you had bought the share for X. So, you spent an amount of X, and now the assumption was that P A minus C A plus S0 is greater than X. So, this is going to be greater than X e raised to R T minus X, which is X into e raised to R T minus 1, and this is strictly greater than or equal to 0. So, that means that you again have an arbitrage opportunity, and so your basic assumption here was incorrect, and consequently this relation actually holds. Now, just one more observation before I finish up. Now, here I had used the argument that suppose that the holder of the American option decides to exercise the call option for which you receive an amount of X. In case it is not exercised, then you still have the possibility, because you are the owner of the option where you have the leverage, and so you can actually receive an amount of X by selling the put option, because remember you had bought the put option. So, you can, even if the call option is not exercised as I had assumed here, you can still receive an amount of X by exercising the put option. So, that means your argument here does not change, except that you will have to wait up till time t equal to capital T. Likewise, the same thing here, I have given the argument here by assuming that the American put is exercised and then you buy the share for X. In case the American put is not exercised, then at time t equal to capital T, you can make use of your call option and buy the share for an amount of X. So, you can obviously still get the share for the amount of X, whether the other party exercise the put option or not. If they exercise the put option, well and good, that then you get the share, or in case they do not exercise, then at time t equal to capital T, you can actually decide to buy the share for X. So, next what you look at is that we basically look at a couple of corollaries out of this result. The first corollary is as follows. So, they will be the corollary which take care of dividends. So, remember that we had obtained similar results in case of the European option. So, we will actually state the analogous result in this case in case of American option. So, first of all, let us look at the first corollary. So, this first corollary is the following, that we can show that S0 minus X e raised to minus R capital T is greater than or equal to C A minus P A, and this is greater than or equal to S0 minus X minus div 0. And recollect that where div 0 is the value of the dividend discounted. So, the dividend could be paid at any intermediate time point, but div 0 is going to be the value of the dividend discounted to time 0. And secondly, another relation would be S 0 into x e raised to minus r t greater than or equal to C A minus P A, and this is going to be greater than or equal to S 0 e raised to minus r div into t minus x, where r div is the continuously is the rate of continuously paid dividends. All right. So, we have obtained the results in case of a European option, namely the put call parity and the put call inequality or bounds in case of American option, and we have looked at stating the analogous results for dividend that is actually paid once and dividend that is actually being paid continuously, both in case of European and American option. Now, let us look at a couple of more sort of obvious properties, not just relating to the price of a call and a put option, but just comparing the price of an American call and an European call, and likewise an American put and a European put. So, then here we will have the bounds. So, the obvious inequalities are C E less than or equal to C A and P E less than or equal to P A. And obviously, you can state this because the price of the American option, both in case of a call and a put option, is going to be larger than or greater than or equal to than their corresponding European counterparts, and the simple reason is that because there is a greater leverage in case of American option, and because as a buyer of an American option you have a greater leverage. So, obviously, you have to pay a larger premium, and one can of course also use some no arbitrage argument to prove this. Next, we have another obvious bound, that is C E is going to be greater than or equal to 0 and P E is going to be greater than or equal to 0. So, obviously, this has to be both non-negative because obviously nobody is going to actually pay you for taking up a disadvantageous position. The obvious way of arguing this is that if your CV is less than 0, that means you actually pay the buyer of the option an amount when you are actually having a disadvantageous position, and likewise in case of the a put option. Next is we establish some upper and lower bounds on prices of European call and European put options. So, first of all, we observe that C E is going to be strictly less than S 0. Now, why is this so? It is so because suppose C E is greater than or equal to 0, then what we will do is that we will just write and sell an option. So, you will receive an amount of C E and then we buy a stock for S 0, right. Now, since we have, so that means that here in this case I have made a profit of, or rather I should say balance of C E minus S 0. Now that I have actually made a profit here, but I have a position of obligation because I have written an option, but it does not matter because I have already purchased the stock for S0, and so this means that at time t equal to capital T, I can simply sell the stock for either the strike price X or the prevailing stock price S of capital T. So, this means that at time t equal to 0 I am making this profit, and at time t equal to capital T I am making an additional amount of this X or S of t, depending on whether the call option is exercised or not respectively. All right. So, this means that my profit is going to be C e minus S 0. Remember, I have made this profit at time t equal to 0, which I will of course invest. So, at time t equal to capital T, this will grow to an amount of C e minus S 0 into e raised to R t plus the minimum of S of t and x, which is going to be obviously greater than or equal to greater than 0. So, what we have seen here is we have this one particular bound which is the upper bound. Now, let us look at a lower bound, and that is going to be S 0 minus x e raised to minus R t less than or equal to C e. Remember, this is the upper bound because it puts an upper cap on the price of the option C e, namely S 0, and likewise I will have a lower bound on C e. So, again using the no arbitrage principle, we try to address why this is so. So, we observe the following. Say, recall that C e minus P e is equal to S 0 minus x e raised to minus R t. This was the put call parity. Now, this can be rewritten as P e is equal to C e minus S 0 plus x e raised to minus R t, but we know that the price of the of any option must be greater than or equal to 0. So, this is going to be greater than or equal to 0. So, from here I can use this to be greater than or equal to 0 to show that S 0 minus x e raised to minus R t is going to be less than or equal to C e. All right. So, both these results now that you have obtained the lower and the upper bound, so I can sum this up as a single relation as follows. So, C e is strictly less than S 0, and this is from here going to be greater than or equal to S 0 minus x e raised to minus R t. So, this is a key result that we have obtained. Now, also remember that there was another result, namely that C e is going to be greater than or equal to 0. So, C e actually has two lower bounds 0 and this respectively, and so accordingly we have the following observations. First of all, C e is strictly less than S 0, and but C e now taking into account both these lower bounds can be rewritten as maximum of 0 comma S 0 minus x e raised to minus R t, and this is going to be less than or equal to C e. Likewise, in case of the put option, this is going to be maximum of 0 and minus S 0 plus x e raised to minus R t less than or equal to P e strictly less than x e raised to minus R t. Now, in case of dividends being paid, this relation gets modified to maximum of 0 comma S 0. So, all the S zeros get replaced with S minus div 0. So, this becomes S 0 minus div 0 minus x e raised to R t less than or equal to C e strictly less than, actually I need to correct this is S 0. So, this is S 0 minus div 0, and this relation becomes maximum of 0 minus S 0 plus div 0 plus x c raised to minus r t. This is less than or equal to P e, and this is strictly less than x c raised to minus r t. Now, we state the analogous results on the bounds in case of American option in a similar way. So, analogously, we can show that maximum of 0 and S 0 minus x c raised to minus r t is less than or equal to C A, strictly less than S 0, and maximum of 0 minus S 0 plus x is less than or equal to P A, strictly less than x. And similarly, in case of, so here this is a case when no dividends are paid, and in case of dividends we have similar results, that is maximum of 0 comma s minus div 0 minus x c raised to minus r t comma s 0 minus x. So, the only difference is now that we have an additional term. This is less than or equal to C A, and this is strictly less than S 0, and likewise I have maximum of 0 minus S 0 plus div 0 plus x c raised to minus r t comma minus S 0 plus x. This is strictly less than or equal to P A, which is strictly less than x. Alright, so now what I am going to do is that I am going to state a few results or propositions, and I will actually just do 1 or 2 cases and leave the rest as exercises. So, some propositions, and these propositions are in case of European option. So, the first proposition we state is the following, that if x prime is less than x double prime, that means there are 2 call options, there are 2 options whose strike prices are different, then C e of x prime is strictly greater than C e of x double prime, and P e of x prime is less than P e of x double prime. Now, the results are very sort of obvious why this is true. See, for example, here you understand that you have x prime, which is a strike price, and which is less than x double prime. That means the price of an option with the strike price x prime, the price for this would be for the call option is C e of x prime, and for x double prime this is going to be C e of x double prime. Now, what happens is that when x prime is less than x double prime, it means that it gives the holder of the European call option to purchase the underlying asset for a price x prime. Now, since in this case x prime is actually less than x double prime, this means that in the second case the purchaser of the option, if they exercise, will have to exercise and buy the underlying asset for a higher price, and which means that in that case they should expect to actually pay a lower premium, which is why the price of the option in case of the higher strike price is actually going to be lower than when the strike price is lower. And a similar argument can actually be made use for this particular inequality. Okay. Now, we look at another proposition. If x prime is less than x double prime as before, then C e of x prime minus C e of x double prime, this is strictly less than e raised to minus r t into x double prime minus x prime, and P e of x double prime minus P e of x prime is strictly less than e raised to minus r t into x double prime minus x prime. Thirdly, let us look at another proposition. Again, we let x prime be less than x double prime, and let alpha, so we choose some alpha in 0 1, then Ce of alpha x prime plus 1 minus alpha x double prime, this is less than or equal to alpha Ce of x prime plus 1 minus alpha Ce of x double prime, and Pe of alpha x prime plus 1 minus alpha x double prime is going to be less than or equal to alpha Pe of x prime plus 1 minus alpha Pe of x double prime. So, this is to say that Ce of x and Pe of x are convex functions of x. Next, we state this proposition 4. Now, here we assume that S prime is less than S double prime, then Ce of S prime is going to be less than Ce of S double prime, and Pe of S prime is going to be strictly greater than Pe of S double prime. Now, another relation, again let S prime be less than S double prime, then just as in case with the strike price, we obtain a similar relation of Ce of S double prime minus Ce of S prime is going to be strictly less than S double prime minus S prime, and Pe of S prime minus Pe of S double prime is strictly less than S double prime minus S prime. Finally, one last proposition, again let S prime less than S double prime. If we have an alpha in 0 1, then Ce of alpha S prime plus 1 minus alpha S double prime is less than or equal to alpha Ce of S prime plus 1 minus alpha Ce of S double prime, and Pe of alpha S prime plus 1 minus alpha S double prime, this is less than or equal to alpha Pe of S prime plus 1 minus alpha Pe of S double prime. So, that means the put and call prices in case of the European option are convex functions of S. Okay, now we move next on to the analogous results for American options. One, if x prime is less than x double prime, then we have Ca of x prime is greater than Ca of x double prime. The argument is very similar to that in case of put option. Intuitively, you can see that in case of European option, you can intuitively see that, and Pa of x prime is going to be less than Pa of x double prime. The second proposition is, if x prime less than x double prime, then Ca of x prime minus Ca of x double prime is less than x double prime minus x, and Pa of x double prime minus P of x prime is strictly less than x double prime minus x prime. Now, for the convexity proof, suppose x prime is less than x double prime and we let alpha in 0 1, then Ca of the linear combination alpha x prime plus 1 minus alpha x double prime is less than or equal to the linear combination of the prices Ca of x prime and Ca of x double prime. And likewise, in case of the American put option, we have an analogous result. Similarly, in case we have S prime less than S double prime, then C A of S prime is strictly less than C A of S double prime, and P A of S prime is strictly greater than P A of S double prime. Again, when I have S prime less than S double prime, then C A of S double prime minus C A of S prime is less than S double prime minus S prime, and P A of S prime minus P A of S double prime is strictly less than S double prime minus S prime. And finally, for the last case, when S prime is less than S double prime and let alpha belongs to 0 1, then we have C A of alpha S prime plus 1 minus alpha S double prime. This is less than or equal to alpha C A of S prime plus 1 minus alpha C A of S double prime, and P A of alpha S prime plus 1 minus alpha S double prime is less than or equal to alpha P A of S prime plus 1 minus alpha P A of S double prime. So, finally, we come to what is known as the time value of options. So, we say that at time t, a call option with strike price x is 1 in the money if S t is greater than x, at the money if S t is equal to x, and out of the money if S t is less than x. So, if you observe carefully here, this is a statement that I am making in general for a call option. So, both in case of a European call and an American call option. So, I say it is in the money because S t greater than x here signifies a situation where if the holder of the option exercises at that particular time point, they will make a profit of S t minus x. Likewise, at the money means that it is essentially some sort of an equilibrium where there is neither loss nor gain if the exercise actually takes place at time t, and out of money means that there is no incentive for the holder of the option to actually exercise the option, because your prevailing price of S t in the market is less than the price that is actually agreed upon. In a similar way, for a put option, we say that it is in the money, and is in the money when the owner of the put option stands to gain, which is when S of t is strictly less than x. It is at the money when both of them are identical, S of t is equal to x, and it is out of the money if the holder of the option has nothing to gain, that means it is when S t is strictly greater than x. All right. So, this brings us to a definition. At time some t less than or equal to t, that means on or before expiration, the intrinsic value of a call option with strike price of x is equal to S of t minus x plus. So, that means the call option will be in the money if this holds, and at the intrinsic value. So, at time t less than or equal to capital T, the intrinsic value. So, it is essentially the payoff at any given point of time t, not necessarily only at the final time. So, it is the intrinsic value of a put option with strike x is equal to x minus st plus. So, this means that when you are out of money or when you are at the money, then in both cases the intrinsic value is equal to 0. So, now we will talk about the time value of an option. So, the time value of an option is the difference between the price of the option and its intrinsic value. So, for European call, this is going to be C e of t minus S t minus x plus. For a European put, this is going to be P e of t x minus S t plus. Now, in case of American call, this is going to be C a of t minus S t minus x plus, and in case of American put, this is going to be P a of t minus x minus S t of plus. Okay, this concludes our discussion about the various properties of options. Recall that in the previous class we had talked about the put call parity, which was the equality that connected the price of the European call and put option and the strike price, and included the current value of the stock and what is going to be the time capital T for expiration. In today's class, we have extended this to an inequality which is analogous to the put call parity. We looked at bounds on the prices of the European call and American call, as well as European put and American put options, namely the lower and the upper bounds, and we stated a large class of properties, especially bound properties in case of both call and put options for both European and American type. And finally, we talked about the intrinsic value of the option, which leads us to the definition of what is the time value of an option. So, this concludes our discussion on properties of derivatives, namely forwards, futures and options. Thank you for watching.